The following video is on curve sketching. The old methods that we had for drawing the graphs of functions were things like plugging in numbers and trying to plot them, or knowing the shifts and stretches of known functions. So, for example, if I knew the graph of sine x, I could graph sine x plus 1. Graphing calculators are often used. But each of these are flawed methods, and in this video we will see why. For the plug and plot method, all we get are a finite number of points, and we use those to connect the dots and make guesses at what happens in between. But what happens if connecting the dots doesn't tell us the whole story? For example, instead of the purple line that we saw connecting the blue dots, what if it's supposed to be this red line? With plugging in and plotting, you're guessing which values, or you're guessing what happens in between the values that you've plotted. So to be more precise, you need to choose more and more values, but that takes more and more time. Furthermore, you still might not get the right values that show you really what's happening because you're only making guesses about the behavior of the graph everywhere else. So for example, what if something crazy happens at x equals a million, but you didn't know to check x equals a million? For shifts and stretches of known functions, first you must actually know what the graph of the original function is. In order to do that, you have to trust what your teachers have told you. So why is the graph of f of x equals the absolute value of x the following? Well, I guess your teachers have told you that in the past. Also, this doesn't work for all functions. For example, if I have the function 3 times the natural log of 5x minus sine of e to the 10x squared, we don't know how to graph that because we don't know how to do shifts and stretches of all of these functions combined. Graphing calculators are actually the worst. Graphing calculators only show you a tiny window, which might not show you all the behavior of the function. So for example, the function might look like this in the tiny window that you're looking at, but if we zoom out, maybe it starts to decrease. But you wouldn't have known that by just looking at your graphing calculator. It's also hard to study local behavior on graphing calculators. So for example, the function might look like this, but if we zoom in on this graph really close, maybe we notice that there's a little dip. We wouldn't have seen that from the original projection of the graph. We would have to know where to zoom in and how far to zoom in order to see it. Furthermore, you must remember to bring your graphing calculator. It sucks when you're trying to graph something with your graphing calculator and you don't have it with you. Finally, graphing calculators are very expensive. The good thing is that they can do a lot of fancy things nowadays that they weren't able to do before, back when I was in school. But the bad thing is they're still very expensive, and we will see in this chapter that we're able to do even more than a graphing calculator can do with just a basic 75-cent calculator that can add, subtract, multiply, and divide. Calculus is going to be our secret. Calculus is going to show us only the interesting points of a function. It's going to tell us the global and local behavior of the function. And it's also not going to require anything more than basic calculators doing add, subtracting, multiplication, and division, and our brains. Furthermore, calculus takes very little time if you practice a lot. So in this chapter, we're going to see how to use calculus to graph functions. We're going to build this up slowly over several lessons. So the first lesson that we'll look at are how to find local extreme values and global extreme values.